Hello everyone, welcome to what will be pre-lecture 15. Just a reminder that I will not be with you in class on Friday, nor will I have office hours, but hopefully this lecture can serve as a good way for you to review some things. As this says, we're pretty much doing a review today of different bonding and polarity ideas that we've covered in the last week. And so I want to start that even with the title slide here, just showing you kind of a different way we can represent polarity. So you'll notice here there's a partial positive and a partial negative shown here with an unequal distribution of electrons. So this would be another way that we could visualize having a polar bond where we have our more electronegative atom right here, our less electronegative atom right there, and we have one side of the molecule that has that negative and one side that has that positive, though they're not fully positive or negative, just partially. Okay, so we're going to keep going with that. Basically, by the end of this lecture, you should be able to draw a correct Lewis structure in 3 dimensions, describe its geometry, hybridization, and polarity. And so hopefully those are all things that you have some idea of doing, but this lecture will help solidify that. Okay, so wanted to start out by showing this. It's basically a different representation of some of the graphics that we've seen before. I'm going to cross out this one here at the bottom because you don't need to know about that. But if we look at these, our far left column here shows us what this calls an electronic geometry, and that's the term I'm going to use in the future. That's basically if we just have bonds, no lone pairs around our central atom, we can call that an electronic geometry. And as you go down here, this is if you have 2 bonds, 3 bonds, 4 bonds, 5 bonds, or 6 bonds, right? And those are geometries that we've covered. Hopefully they're very familiar right now. But where things, of course, get trickier are our molecular geometries. And that's when we start to bring in these lone pairs, shown here by kind of these blue orbitals. And so you'll notice that the kind of numbering for these rows stays consistent as we go across here, but we're just trading out one of our bonds or 2 of our bonds or 3 of our bonds for lone pairs. Okay? And so just a couple trends I'll point out here is that if we end up replacing enough of our lone pairs, either 4 or 3, or replacing our bonds with lone pairs, our geometry ends up going back to being linear, right, in a lot of cases. And so those are, I know, kind of tricky ones to remember. Otherwise, I think it's just all about practice. And so hopefully through this lecture and through the homework, you'll be able to essentially memorize this table and what it represents and how you can use it to represent geometries. Okay. Along with that, just wanted to show this graphic again. It's another example of how we bring geometry into our understanding of things. And this is, of course, related to hybridization. And so whatever our geometry is or our number of bonding domains, I should say, which of course is related to our geometry, that's how many orbitals we need. So for anything with 4 bonding domains, we're going to have sp3 hybridization, right? If we have 5 bonding domains, we're going to have dsp3 and so on and so forth. Okay, so that was something that I think I mentioned last class. Just wanted to make sure that that point got conveyed though. Another thing to review is our understanding of electronegativity. So this is a very big point in not just general chemistry, but really any chemistry you're going to see. That's why I really want to make sure that you learn it. You obviously don't have to memorize these values, but the things I want to review here is that electronegativity goes up as we go up the periodic table. It also increases as we go across. Something else I'll say, you don't need to know electronegativity for our noble gases. We're just not concerned about their electronegativity with compounds here. The other thing I want to point out is fluorine, rather, is our most electronegative. And so people ask me, you know, if I don't know what the electronegativity is, how can I have a good estimate? I, as a general guide, just try and figure out how close it is to fluorine. So things like oxygen, sulfur, chlorine all have very high electronegativities. Nitrogen, of course, very high as well. And so those are the most electronegative kind of block that we're going to deal with. And then, of course, on the opposite end, things like cesium have the least amount of electronegativity. Okay? And I found another representation of that in the periodic table, things that are represented in color coding this time. So same things I was just saying. And another thing I want to remind you all of is that anytime we have a CH bond, that is considered nonpolar. Okay? And part of the reason we can draw that distinction is a rule that I'm going to give you right here that some people have asked for. How do we know when we go from having a polar bond to a nonpolar bond? We're going to say that electronegativity differences greater than about 0.4 in our electronegativity scale are going to lead to the formation of polar bonds. Once we get to another point of having an electronegativity difference greater than about 1.5, at that point we might even start to consider the compound to be ionic, but there is basically a spectrum there, and so it might not be purely ionic. There are definitely some exceptions there, and so as a general rule for ionic compounds, think about metals bonding with nonmetals. That tends to be our best indicator as to whether or not something is ionic or not. Okay? Another thing I want to point out here is a different way we can represent polarity in bonds using these arrows here, where the more positive side or the less electronegative atom, we're going to draw basically a plus sign there. And then on our other side, for our more electronegative atom, that's going to be where our arrow points. And so if we have this boron-fluorine bond, we would say that our fluorine is, of course, most electronegative, and so our polarity of that bond would point that way. Okay? And let's do some practice with this, some stuff that you might see similar to our quiz on Monday. So draw Lewis structures, assign molecular and electronic geometries, and determine if the molecule is polar for the following molecules. So H2O, hopefully the Lewis structure is a piece of cake by this point for H2O. We have oxygen, and then we're going to put 2 lone pairs in order to give oxygen our octet, fill all of our valence shells. And so if we were to look on our chart and assign a molecular and electronic geometry, electronic geometries are just essentially whatever the number of bonding groups is. And so because we have 2 bonds, 2 non-bonding groups, we would say we have a total of 4 bonding domains. And domains, if I can spell, and that is going to be a tetrahedral electronic geometry. Tetrahedral. And then if we think about that we have 2 bonds and 2 non-bonds, that's going to be our molecular geometry. This is going to be a bent molecular geometry, right? And of course, if we were to go back to our table right here and look at that, when we have 2 bonds, 2 non-bonds, that is going to be a bent geometry. Okay? I'm going to change color here for a sec to show you polarity. So if we were to show our polarity, we would say that the side with our electron lone pairs tends to be negative. And so anything with electron lone pairs is going to be negative. Oxygen is, of course, more electronegative than hydrogen, so we would say our hydrogens have a partial positive charge, whereas our oxygen is a partial negative, meaning that overall this is a polar molecule, indeed. Okay? The molecule itself, as well as the bonds, are polar. If we do our next example of BF3, we can count our valence electrons, 3 from boron, 3 fluorines. Each fluorine has 7, so that should be 21 for a total of 24 valence electrons. And if we put BF3 around and add in our lone pairs for our fluorines, then count that all up, it should be 8, 16, 24 valence electrons. And hopefully you remember that boron is one of our molecules that, or atoms, that is fine just having 6 electrons. So this would actually be our complete Lewis structure. And because we only have bonding groups, our molecular and electronic geometries are going to be the same. And it's going to be a flat molecule, so we don't need to put wedges or dashes. This is called trigonal planar, right? Of course, if you were to look back at the table, you would see that that is its geometry. As far as bond polarity goes, we know fluorine is more electronegative than boron, and so we can draw our arrows if we wanted to. That would also mean that our boron could take on a partial positive, our fluorine's partial negatives, but this is where we have to take into account our geometry. So because we have 3 fluorine bonds or boron fluorine bonds that are all pulling in equal and opposite directions, what actually happens here is all of the bond polarities cancel out. So this partial negative and partial positive, or all the partial negatives basically cancel out, and the molecule overall ends up being non-polar. Okay, so that's tricky. When you have polar bonds, but all those bonds pull in equal and opposite directions, that makes things non-polar. Okay? All right, I'm going to go on to the next example, SF4. So S has 6 valence electrons, fluorine has 7, like we said, and if we multiply that by 4, we get 28. So this should have 34 valence electrons. If we put our sulfur in the middle, I'm going to say, let's build a tetrahedral. So when we have 4 bonding groups, we can build our tetrahedral by having 2 of our fluorines just with normal bonds here. Then we do 1 dash for our fluorine and 1 wedge for our last group, and that is a tetrahedral. And if we count up our electrons here, we have 8, 16, also, sorry, I just want to erase this here. Looks kind of like a double bond. Let me make that a single bond. So we have 8, 16, 24, and 32 electrons in this structure. So we're missing 2, so we'd have to put those on the sulfur. What this means is that we don't have a tetrahedral geometry, but we actually have 4 bonding groups, 1 non-bonding group, for a total of 5 bonding domains. So I'm actually going to erase this Lewis structure, treat it as a draft. And if I wanted to, as I'm learning, I could certainly go back and look at my table to figure out what our geometry is. But let's say I'm a very wise student at this point and have figured out that when I have 4 bonding groups and 1 non-bonding group, I know what my geometry is going to look like. It's going to look like this, where we have our lone pair on one side and then our 4 bonds, 2 in the plane and 1 going behind and 1 coming out in front. And we would call this a seesaw geometry, everyone's favorite. It's a good name. And so that is a seesaw geometry. And if we were to assess the polarity here, like I said previously, anytime we have an electron lone pair, that's going to be a partial negative. But, of course, our fluorines are more electronegative, so those are also going to have partial negative charges. And so the overall polarity of this molecule would be polar because things are not equally distributed. Again, on one side, we just have this lone pair here. But it would probably be overall less polar than something like water that's very clearly polar. Okay, so that's some examples for you, and probably have something similar on your quiz on Monday. Wanted to cover one more topic, and that's bringing together ionic compounds to make neutral salts. And so we have these following pairs of ions. Also, this is not the right one. Sorry about that typo. This should be NO3 minus instead of NO3 minus. And so what we want to do here is figure out the ratio of cation to anion for each of these compounds. And so if we have a 2+ charge for magnesium and a 1- charge for nitrate, we're going to need 2 of those nitrates in order to balance the 2+ charge. And so we can put our nitrate in parentheses there and say that we need 2 of those in order to balance. So we have 2+ charge for magnesium. Now we have 2 times -1 for nitrate to balance it, and again, make a neutral compound. Okay? Another way we could think about this, as was how my high school chemistry teacher taught me, is if we look at charges, we can do what he called the crisscross method, where we essentially take what's at the top for one of our ions and trade it to be the coefficient at the bottom. So iron would be iron 2 because of our 2- charge on sulfate. And then sulfate, SO4 2-, we would need 3 of, because we have the 3+ from iron. And so then we would have 2 times a 3+ charge to be 6+ total. Our sulfate would be 3 times the 2- charge for a 6- total, and so overall that would be neutral, right? Finally, we have sodium and carbonate, 2-, and so in this case, NaCO3, and we would need a 2 there in front of the sodium to balance that out, again, if we crisscrossed our charges. Okay? All right, hopefully that was helpful in shoring up some of our understanding of ionic bonds, as well as tying together geometries, hybridization, and Lewis structures. If you have any questions, please do let me know. Otherwise, I hope you have a good weekend, and I will see you on Monday.